When were the first terrestrial planets possible? How does the expanding universe win out over gravity? And can black holes have Lagrange points? All these questions and more in The Question Show. It's time for The Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Agent Dark Booty. When would the first terrestrial planets have formed? So we here in the solar system are on planet Earth. Planet Earth formed about 4.5 billion years ago when the sun and all of the planets formed. And so obviously we have a planet that is large enough, has the right rocky materials to form a terrestrial planet and to be able to support life. Good news. But, is this the earliest that a planet could have formed? 4.5 billion years. When you think about the universe is 13.8 billion years old. 4.5 billion years, that only gets to like the 9 billion year mark of the universe. So could you have had planets earlier than that? And the answer is absolutely. And when you sort of go back to the beginning of the universe, you've got sort of the light elements. The universe was mostly hydrogen and some helium with sort of trace amounts of other heavier elements, which astronomers call metals. So, anything beyond helium on the periodic table of elements, astronomers consider to be metal. And you got like just trace amounts of some of those, like lithium, beryllium, things like that, shortly after the Big Bang. But then it was like that first generation of stars, what they call the population 3 stars, that would have been the furnaces to produce a lot of the earlier, heavier elements. And so you've got these first stars made of primordial hydrogen, helium. They could have grown to unimaginable sizes and masses. And then they would detonate a supernova probably within a couple of million years. And then you would get more of them forming and you would sort of already start to cycle up. It's called nucleosynthesis. And so within about, it's estimated, it's theorized, although it hasn't been directly detected, that you probably could get enough heavier elements to start forming planets within 100 to 200 million years after the Big Bang, that you had enough cycles of supernova going off where you've got material and then you've got eventually like actual stellar nebulae, you've got planetary systems forming around stars within just a couple of 100 million years of the Big Bang. Definitely within the first billion years or so. Now, what is the oldest planetary system that we have ever discovered? And in fact, we've found a planetary system that is 11.2 billion years old. And it's called KOI 3158. And so when you think about that, like if we've seen a planetary system where the planets were formed just about 2 billion years after the Big Bang. And that's in our relative neighborhood, something discovered by Kepler within the last, couple of decades, then there must be older planetary systems out there in the Milky Way and out there in the entire universe. But another kind of really interesting question is, like, when could you get terrestrial planets where you could have the kinds of chemicals in the right abundances, the right metals that could give you life? And it's believed that that number actually probably took a lot longer, that sort of for the first few billion years, the kinds of stars that you got and therefore the kinds of planetary systems were lighter, that they were metal poor. And so the terrestrial planets still would have been metal, but they would have been of lighter elements, less iron, more oxygen. And so really, it's believed that only about 2 billion years before the solar system was able to form was at about the age when enough of this nucleosynthesis, enough colliding neutron stars, enough supernova had gone off to enrich the environment that you could get the kinds of planets that we're more familiar with, the kinds of places like Earth. But still, like 2 billion years, this kind of brings us back to the Fermi paradox, where like 2 billion years is a long time. That's a lot of years for a civilization to form, become advanced, colonize the galaxy. And so always, where is everybody? Sakura Kinomoto 6195. Humanity's ability to go to space is on an exponential curve. This is a pipe dream. Just remember when humanity was able to fly to the moon, it was nearly 60 years ago, and it goes on like that. So this is a response to a QA that I gave a couple of weeks ago where I was talking about how, people always say that I'm so skeptical about the future of humanity's space. Do I think we're going to have a city on Mars? Do I think we're going to be living across the solar system? And I say that I don't think that the current plans for colonizing Mars, to build a city on Mars of 1 million people in the near term is realistic, because we don't know how to do many of the things. There's no profit margin. There's no way to fund this process. It can be done at enormous expense for decades, for hundreds of years. Like it's too soon. And that we do things like build giant cities or develop technologies or come up with ways to mine the ground or drill for oil or all this kind of stuff at appropriate times along the technology curve and along the infrastructure curve and along the sort of gross domestic product curve. And we are too early. And in fact, the Apollo missions, which was the example that this person gave in that comment, that was too early. And so just to give you some context, when the US decided they were going to put a man on the moon, they spent, in inflation adjusted dollars for 2020, $257 billion on the Apollo program. It was a huge amount of money as a fraction of the United States budget. Today, the US spends about $20 billion a year on NASA, and that funds all of the things they're doing, maintaining the space station, maintaining various missions, aviation, safety, things like that. And so you add up the total budget that's been spent on SLS, it's about $25 billion. When you add up the money that's been spent on Orion, it's a little over $20 billion. There's a couple of other contracts. So you're looking at, and this is like, these various programs have been around for 15 years. Like they've been developed at at relatively low cost. And so you're going to always be able to have these advances, like having a human set foot on the moon, but it wasn't done because it was the right profitable thing to do. It was a show of strength by the United States, and they paid an enormous cost to do it too early on the technology curve. But here we are in 2025. I got to keep saying that to get it right. And we have 5,000 satellites orbiting around the Earth, and they were done at a profit, right? That you've got mostly they're Starlinks, but you've got lots of other satellite networks that are launching these satellites. And that we're expected, say within the decade, to have 30,000 just Starlinks, maybe 50,000 satellites orbiting around the Earth, and that we are going to be expanding the uses of our various technology. And so while I am not a fan of us colonizing Mars in the near term, if you look at just the exponential growth of our technology over time, then within some point in the future, as long as we continue to grow, then we will be living on other planets. We will be utilizing the resources of the entire solar system. And people have done these relatively conservative estimates. If you just take the gross domestic product of humanity, where it's growing at like 1% per year, and you chart that forward with exponential growth within a couple of 100 years, the only way to support the gross domestic product of that economy is that you have gone to space, that you are mining asteroids, that you are living on Mars, that you are, you're living across the solar system. And, obviously there's no guarantee that the growth of our economy will continue on into the far future. And there's no sort of, there are many people who argue that that's actually not a good thing, that it's just not sustainable, that you'll get to a certain point that you will start to be, tearing apart planets and moons. And even then, that's not going to be enough. And at some point, we will reach some limit to growth. And we know what happens in the natural world. When you reach limits of growth, you get starvation, you get death. So, we hopefully will be able to figure out a way to grow in a way that's sustainable with the resources of the solar system. But I think to not consider the growth of humanity and our economy in this exponential scale is to not be thinking realistically about what the future holds. I think about this book by Ray Kurzweil called The Age of Spiritual Machines. And he was talking about this future when computers are going to be sort of very intelligent and will be the equivalent of minds like human beings. And I read this book in the year 2000, I think. And he just looked at the growth of computing, and then he calculated roughly what is the sort of amount of computing that's required to support a human brain. And he figured that there would be, by 2029, there would be the equivalent of a human brain, purely from this exponential growth curve. And, here we are in 2025, feeling like, as you chat with large language models, and you can, many of them will pass the Turing test. You start to feel that, okay, these, with nothing more than just looking at the growth of a growth curve, that the future feels inevitable. And so, and so I think, when people see me as being a skeptical, I'm poo-pooing us going and living on Mars, it's just the time frame that you want it done in your lifetime. It's probably not going to happen in your lifetime. But it is inevitable, as well as our, as long as we continue, as long as we don't wipe ourselves out, we will reach other star systems. We will reach out to the entire galaxy. We will eventually reach out to the entire reachable universe, as long as we continue to grow, or, unless we don't wipe ourselves out. And hopefully we can figure out a way to sustainably do this. NYBSFP. If the universe is expanding and everything is moving away from everything else on a galactic scale, how can we also see evidence of galaxies crashing into each other? This is the classic question, which is that if the universe is expanding and everything is moving away from each other, why is Andromeda moving towards us? And yes, Andromeda is moving towards us. And in several billion years, Andromeda will crash into the Milky Way and they will form this larger elliptical galaxy. But there are only a couple of galaxies that are moving towards us. The other one is M33 and other dwarf galaxies. But at the largest scale, everything else in the universe is moving away from us, and everything in the universe is moving away from each other. At the smallest scales, Andromeda, 2.5 million light years away from us, is gravitationally bound, or I guess we're gravitationally bound to Andromeda. We're going to crash into Andromeda. We should say that the larger, more massive galaxy is attracted to us. Let's be real here. But the line is about 5 million light years away. And so if you get this galaxy that's about 5 million light years away from us, it is over the line, and that the amount of expansion that is happening in the universe is going to carry that galaxy away from us faster than the force of gravity that's trying to pull those galaxies towards the local group, or us towards that group. Again, don't know who's in charge here. But then as you get those distances get larger, then it's absolutely overwhelming. And so there's probably places where you've got this expansion of the universe. You've got galaxies that are perfectly balanced at some number. It's, I don't know what the exact number is. It's going to be somewhere between 4 and 5 million light years away, where the galaxies are trying to move towards each other, but the space is expanding apart and holding them apart, and they appear to hover. It's like being on those movators when you're in the airport and you're walking along. And so imagine, you're walking on one of these pathways in the opposite direction, and your friend is walking beside you just on the ground. And so you are trying to walk towards them, but the treadmill is pulling you away from them. And maybe you walk quickly to perfectly balance things out. And so that's what's happening in the universe, that there's always these two forces. There's the force of gravity that's pulling things together. There's just the expansion of the universe that's pushing things apart. And in various places where things are relatively close to each other, then it's the gravity that wins out and they're able to pull each other together and form these larger objects. But in other places where this expansion is what wins out, then things are pulled over the cosmic horizon and they will never be able to reach. So that's why we see galaxy collisions. They got too close. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to our recent newcomers: Bruce Polson, Nigel Universe, Del Tor, Joe Tranzini, Rawl, and Gunnar Heiberg. Join the club at patreon.com/universe today. Manos Anasis. Hello, I'm a 15-year-old who wants to become a space engineer. I would like to find out a way to help now. How can a teenager contribute to space exploration? It all depends on whether you want to try and get involved on projects today or whether you want to invest your time to gain the skills to become an engineer down the road, because time spent today on various hobbies is time and focus taken away from your study and actually becoming an engineer. But I think it's like an interesting question, and you're sort of like, it's hard to be patient. If you want to become an engineer, you're looking at finishing your high school, you're looking at going to engineering for 4 years to get your bachelor's degree in engineering. You're probably going to then go and get your master's degree at, say, an aerospace firm or something like that. And then you're going to decide, are you happy with a master's degree in aerospace engineering to become an engineer at a space agency? Do you want to keep going to some more specialized thing into plasma physics or supercomputing or something like that? Then there's maybe you can go out and get your PhD. And so you could be looking at 10 years of education plus after you finish high school, before you're finally able to contribute, which is the way I'm sort of sure you're looking at this. But that's not true. There are so many ways that you can internalize the fundamentals of spaceflight and space exploration. There are books that you can read that you can sort of gain a sort of a different understanding. There are video games that you can play, like the Kerbal Space Program, where you can practice different underlying concepts in orbital mechanics and stage spaceflight and doing gravitational assists and building various structures in space and understanding what it takes. There are really interesting high school level engineering challenges that the various space agencies put together, like ESA will do various competitions from high schoolers. NASA does competitions from high schoolers. And I think, like the way you've posed the question is like, how can I help now? And no one needs you to help right now. Everybody wants to help you. And so all of these things exist for you to be able to bring yourself up to speed and get yourself to a place where you can contribute to humanity's future in space. Don't worry too much about trying to do your part. This is the time. You're young. The entire industry wants to help you get ready so that you can then, and invest in you so that then you can play your part. So accept the help. Take advantage of all of the resources that have been made available to you, both privately, both professionally, by universities, by various people who are further along, who want to become your mentor, and learn, soak it all up. Participate in these various challenges, learn these additional technologies, get good grades in school, go to a good university where you can gain these skills, continue to give back once you've reached a certain level of capability to help that next generation get that leg up. So I think it's awesome that you want to know how you can help. But right now, everybody wants to know how they can help you. And so, accept that help and make a difference. Wisp Frog. Are there the same Lagrange points for an object orbiting a black hole? What if it is rotating fast? Finally, a Lagrange point question. I'm so excited. So a black hole is nothing special from a star. It's just that it is more dense. And so you could replace the sun with a black hole of the same mass as the sun, which can't form naturally, but let's say that you could, and the rest of the planets in the solar system would be happy to orbit around this black hole sun. You would still have the exact same Lagrange points. You would have the black hole Earth, L1, L2, L3, L4, L5 Lagrange points. Same with Jupiter. Everything would be exactly the same. And so if you imagine a more realistic black hole, the kind that could form, say, something that has 10 times the mass of the sun, and let's say that it has a star that is orbiting around it that is maybe 1 time the mass of the sun. I mean, the problem is you need to get, like, they have to be very significantly different masses for you to be able to get those Lagrange points. And so the sun is 99.5% of the solar system, and Jupiter is most of the rest. And so you get those Lagrange points when you have this factor of like 200 in mass between the sun and Jupiter. So you would need, like, say, a Jupiter, or like a super Jupiter, or maybe a brown dwarf or something orbiting, or a red dwarf orbiting around this black hole. But yeah, you would get Lagrange points. You could imagine a dwarf galaxy that is orbiting around a supermassive black hole. Supermassive black hole has, say, 100 million times the mass of the sun, and the dwarf galaxy has 1 million times the mass of the sun. And you would get Lagrange points that would be popping up in the same places as you would get here in the solar system. So it's, what's important is that you need to have something with a lot of mass that is orbiting by something with less mass, a fraction of its mass, and that creates the Lagrange points. Gadget to your farm. If a civilization is at our state within 1,000 light years, we would not detect its radio or TV, right? Currently, that's correct. Specifically, you said TV and radio, but I think I'll generalize the question, which is that could we, in our current state, with our current ability to detect, if we were 1,000 light years away, would we be able to detect us in any way, right? And the answer is yes, which is that if we had a James Webb Space Telescope, or if the other us's had a James Webb Space Telescope and they were pointed at the sun, and they were able to differentiate the light coming from the sun and the light coming from planet Earth, they could detect the presence of chlorofluorocarbons in the atmosphere of planet Earth and detect the presence of a technological civilization here on Earth. So that's the most glaring signal that we are giving off currently, is the chemicals we put into our atmosphere that could only have been created by an advanced civilization. But radio is like coming in as a number 2. And with our current suite of technologies, no. Radio waves follow by the inverse square law. And so as radio waves move out into the universe, the farther away you get, the intensity of those radio waves fall dramatically. And so our current best radio telescopes couldn't detect us 1,000 light years away. But there is a next generation radio telescope that is being built right now called the Square Kilometer Array. And this is going to have 1 kilometer of observing area across 2 locations on Earth. So one's going to be in Australia, one is going to be in South America, and together you're going to add up the collecting area of the 2 radio telescopes, and you're going to get 1 square kilometer of observing area. And they are separated by thousands of kilometers, and so they can act like an interferometer to join their observations together. It won't be built for probably another 10 years or so, but when it does come online, the Square Kilometer Array will be so powerful that it could detect the presence of humanity's air traffic control systems. Those are some of the brightest radio sources that human beings emit out into the universe. Way more powerful than us sending television signals or radio signals. And we could detect us about 100 light years away. And so if there was another civilization like humanity that had air traffic control systems and they were generating their signals, when the Square Kilometer Array comes online, it would be able to detect the presence. It could detect you using a cell phone on Mars. It's crazy how powerful this telescope is going to be. So, and then over time, as more telescopes are added to the square kilometer array, it eventually becomes the 2 square kilometer array, the 10 square kilometer array. This is going to get bigger and bigger. Maybe they'll add another site in South America, and you really have this larger and larger telescope that eventually you're going to get the ability to see out to 1,000 light years away. So eventually get out to 10,000 light years away. And then again, obviously, we're going to see these civilizations as they looked in the past, or we're going to listen to their air traffic control systems as they were in the past, but we can make those detections, and we're going to get better and better at that every year. And so you would assume that if there are other civilizations out there, they can detect us, or will be able to. Casper Helfrich. You've often said that you believe we are alone in the universe. Is the thought of being alone scary or a relieving feeling for you? So, people are surprised when I say that I think that we're alone in the universe. And obviously this is not a scientific stand that I'm going to take. This is sort of like a philosophical, personal opinion based on the observations that have been made and on how empty the universe appears to be, how much it seems like just raw wilderness, that we don't see these advanced civilizations gobbling up entire chunks of the universe to turn into their Jupiter-sized blocks of computronium. So like, how do I feel about that? So, I mean, for me, I feel like we have a responsibility to do this right, that we are currently at a time in the history of humanity where we are having a negative impact on the planet, on the biosphere, we are changing the weather, we are changing the climate in a way that is bad for us. It's bad for other creatures as well, but it is definitely bad for us and could have implications for human society down the road. If we increase the sea level, then we destroy some of our cities. If we have lots of people be nomadic, having to leave places where the temperatures are bad, this is all bad. And, it's not the kind of thing that is existential to humanity or existential to life on Earth. It's just bad. We prefer the climate that we evolved in. We prefer the climate that we built our society in. That's the climate that's best for us, and we should try to maintain that climate. So we are, and like, what happens if we don't if we mess this up? What happens if we get really catastrophic about it? What happens if we produce a super virus that kills all humanity and we wipe ourselves out? Well, then, we've used up all of the ready resources on the surface of planet Earth. Maybe the octopuses will show up and build something out of our society, but, we've used all the easy stuff, so they're going to have to drill deep or wait a long time for the Earth to recycle material so that you can make it available. The octopuses and the dolphins and the parrots or the crows will be that next society. And so if the universe has life in it, and life is everywhere, then I don't feel this sense of urgency to be the sort of the group that ensures that that life survives in the universe, that, the aliens at Betelgeuse have got this under control, that, at some point, if we get our act together, we can join the Galactic Federation and play our part in the future of intelligent civilizations in the universe. But if we are alone, if we are the only ones, then we're messing up a really interesting opportunity. We're kind of screwing up what is a chance for the universe to be filled with life, right? Imagine this one tiny, interesting spot of complexity and life appears in the universe, and then under our watch, it goes out again. And then the sun expands and consumes the Earth, and then for the rest of the future of the universe, life never made it past this one planet. And that seems like a shame. I think that the universe is made more interesting by life. And so until we find out, I am super interested in us figuring out the answer to this question. Are we alone in the universe? I report obsessively about radio telescopes that are examining the sky, about possible places to search for life in the solar system, about how we could observe advanced civilizations from afar, because I want to get an answer to that question either way. But I'm also really obsessed with us becoming a solar system spanning civilization, and us being able to become able to move out to other star systems. It's the same motivation, I think, that Jeff Bezos has, that Elon Musk has, that a lot of you watching this have, which is like we want to get our eggs out of this basket and out into other places. I just differ on the time frame, but underlying motivation is that I think the universe is made better by having life, and especially intelligent life, in it. And that I think if it turns out, as we learn more and more about the universe, we find it's empty at the farthest we can see, we actually send spacecraft to other star systems, we don't find any life, then I think it's our responsibility to take life to the cosmos, because if we don't, then life will end with us here on Earth. So that's how I feel about that. And that's sort of, is alone being scary? Being alone is scary. Is being in a populated universe scary? Yeah, that's scary too, because then you're dealing with all of these warring potential competing factors. People may want the atoms in the solar system for their own purposes. That's scary. And the thing that cuts through all of it in both cases is knowledge. The thing that allows us to understand where we are, what is the true nature of this universe that we have found ourselves in. We need to figure out an answer. We need to observe and learn, and then we can take action based on what we've learned. So that's how I feel. All right, those are all the questions that we had this week. Thank you, everyone who put your questions into the YouTube comments, as well as everybody who joined us for the live show. Now, we do a new live show every week, but we do it at a different time. So sometimes we do it in Pacific time, where I live. Sometimes we do it in European time. Sometimes we do it in Australian time. So you're gonna have to check and see when the next live stream is coming up, so you can make sure that you catch it live and join the larger conversation. The show's 2 hours long. It's a lot of fun. All right, I'm going to talk a bit about some of the recent interviews that I've done, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bear Lake Roofing, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Sean Sargent, Spidersup.io, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So I did a couple of really interesting interviews, and when you watch this, 2 of them will be out in the last couple of weeks. A whole bunch more are coming. And the thing that I'm really obsessed with right now is abiogenesis, the search for life. What are the limitations on life? How would we recognize life, not only as we know it, but life as we don't know it? And so I've had a recent interview about sort of phosphorus as a limiting element for life. And I've got a really interesting one coming out shortly, talking about sort of the underlying logic of life. If you go back to first principles and think about what would it take for life in terms of a sort of thermodynamic level, as well as information storage, cellular, things like that. How could you recognize life, even if it's not something like what we evolved with here on Earth? So I'm going to put links to the various interview playlists that I have here on the channel, and I definitely recommend you watch some of these. They're really fascinating.